Okay, so here's the winter poster assignment um, from Adam, and this is I also worked on this with Patricia Miranda from first period. So here we in this side, the red side, we have constant velocity, and we have three graphs: position, velocity, and acceleration. For the position, the slope is going to be slanted and positive, and that means for every second that passes, the object in motion travels a certain number of meters. And the equation for that would be right here: position equals blank numbers of meters per second times time, sorry, plus the vertical intercept. So right here we have velocity, and it's a straight line, and the reason for that is because the slope of the position time graph is linear and positive, the slope of the velocity graph is going to be constant. So nothing's changing with the slope. And the shaded part right here is the area, which is displacement, and that's velocity times time. And over here we have the acceleration graph, and there's nothing in it because since the velocity is constant, then that means there is no acceleration, and nothing could be determined from it. So in the bottom right here, we have a force diagram and a vector sum diagram. The force diagram, there's four forces acting upon each other, and if you add them up in the vector sum diagram, then they all add to zero because there shouldn't be an acceleration, and therefore there shouldn't be a net force. So in this side, we have constant acceleration, and all the explanations, well, the explanations for position right here and velocity right here, these two, they're basically the same as these ones, but the only thing that's different is the slope of the graphs, because the slope of the position time graph is curved this time, and because it's curved, then that means um, the velocity time graph is going to be slanted and linear. So and the area is going to change because this shaded part right here is again displacement, but it shows the change in position. It's going to be one half times uh, one half time times velocity. And for this acceleration graph, because the velocity is linear and positive, um, the acceleration this time is going to be constant. And since there's an area for this one which shows the change in velocity, which is basically acceleration times time. And we have another force diagram, the same one as this one, and a vector sum diagram, but this time um, the friction is a little bit shorter, and that's if you put that in a vector sum diagram, then it can't add up to zero, so you need that net force to make everything add up to zero. And since there is a net force, then that means there is an acceleration. And right here we have Newton's third law, where a force is basically one half of an interaction, and the force of one object object is the same as the force being exerted by a second object. And when two when you have two objects and one object a bigger mass and the second object has a lighter mass, the forces are still going to be the same. They're going to um, exert the same amount of force on each other, but um, the one with less mass is going to probably be back or something because it has lesser mass despite the same force being exerted as the first force. And yeah.